US Physics Olympiad, year 2017, USAPHO, final round. That was 2 parts for this round. First part was 4 problems A, and the second part was 2 problems B. For each part that was given 60 minutes. So if you want to see all these problems, please subscribe for this channel. Problem A1. A pair of wedges are located on a horizontal surface. The coefficient of friction, both sliding and static, between the wedges is nu. The coefficient of friction between the bottom wedge B and the horizontal surface is nu, and the angle of the wedge is theta. The mass of the top wedge A is m, and the mass of the bottom wedge B is 2m. A horizontal force F directed to the left is applied to the bottom wedge as shown in the figure. Determine the range of values for F so that the top wedge does not slip on the bottom wedge. Express your answers in terms of any of all of m, g, theta and mu. Solution for problem A1. First, let's sketch the free body diagram. Suppose that force F is big enough that this top wedge try to move up. It means that the force of friction will be going down, and the normal force is perpendicular to this surface. Now we can write equations. For horizontal motion we have 3ma equal force F minus force of friction, which is 3 mu mg. Also we can write equations for motion of this top wedge. For horizontal motion we have ma equal normal force sine theta plus force of friction cosine theta. And for vertical part we have normal force multiplied by cosine theta, that's equalized by gravity force mg plus force of friction F multiplied by sine theta. And in a critical case we have force of friction equal mu multiplied by normal force. And also we have from this first equation that acceleration equal force F over 3m minus mu g. Now we can put these expressions to our equations for motion of this top wedge. And we have these 2 equations. From the second equation we can express normal force, which is equal this expression. And now we can insert this expression here and finally find what is maximum possible force F. That will be this expression, and after some reductions we have this answer. This is answer for maximum possible force F. Let's do the same for minimum possible when this up wedge try to move down. In that case force of friction has opposite sign, and we can rewrite these equations. Now force of friction has opposite sign. This is why we have for motion of this top wedge these 2 expressions. And we do the same steps. Now when we insert force of friction mu n to these equations and acceleration, we have these 2 equations, and from this first equation again we can express what is normal force. That will be this expression. And the last step is to put this normal force here. And finally for force F we have this expression, which is solution for smallest possible force of F. That was a solution for problem A1. There is other way to solve this problem, and we can use a so-called non-inertial frame of reference. If we use a frame of reference which is moving to the left with acceleration a, we can use this dynamic with a non-inertial frame of reference. In this new frame of reference, this horizontal arrow, that's the acceleration a, which is going to the right. This vertical arrow, that's acceleration g, and the red arrow, it's a direction for net effective acceleration, which is going in this system. And now we see that effective angle will be theta minus this angle between red arrow and the vertical. And we have this expression for this angle. We have tangent phi equal a over g. And now we can find what is tangent for this effective angle, which is theta minus phi. So we have for tangent theta minus phi, that's equal this expression. But this tangent for critical acceleration equal mu, coefficient of friction. Mu equal this expression, and now we have tangent phi equal mu minimum over g, which is this expression. And this minimum acceleration we can use to find what is minimum force F. That's the approach for using non-inertial frame of reference. Same way we can find what is maximum possible acceleration and maximum possible force F. Now we have angle phi greater than theta, and we have maximum possible acceleration, and we have to find what is tangent phi minus theta, and that will be critical angle equal mu. And now tangent phi equal a maximum over g, which is this expression, and from here we can find what is maximum force F. That was a solution using non-inertial frame of reference. And also we can mention that if initially tangent theta less than mu, the minimum force equals 0, because we already not reached the critical angle. Problem A2. Consider two objects with equal heat capacitance C and the initial temperatures T1 and T2. A Carnot engine is run using these objects as its hot and cold reservoirs until they are at equal temperatures. Assume that the temperature changes of both the hot and cold reservoirs is very small compared to the temperature during any one cycle of the Carnot engine. Question A. Find the final temperature Tf of the two objects and the total work W done by the engine. Now consider three objects with equal and constant heat capacity at initial temperatures. 100 Kelvin, T2 equal 300 Kelvin, and T3 equal 300 Kelvin. Suppose we wish to raise the temperature of the third object. To do this, we could run a Carnot engine between the first and the second objects, extracting work W. This work can then be dissipated as heat to raise the temperature of the third object. Even better, it can be stored and used to run a Carnot engine between the first and the third object in reverse, which pumps heat into the third object. Assume that all work produced by running engines can be stored and used without dissipation. Question B. Find the minimum temperature TL to which the first object can be lowered. Question C. Find the maximum temperature TH to which the third object can be raised. Solution for problem. Question A. During Carnot cycle we have 4 processes. 2 processes are adiabatic, during which delta Q is 0, and 2 isothermal processes when we have this equation. Because this Carnot cycle is a closed cycle and reversible, we have a total change of entropy is 0. And this change of entropy, it's only during isothermal process. So we have ds1 plus ds2 equal this expression, and this equal 0. And now, because heat capacitance is the same for both objects with the temperature T1 and T2, we have dq1 equal c dt1 and the dq2 equal c dt2. Now we can put them in this equation and find that during one cycle we have this equation where delta T1 and delta T2 is very small, and we can integrate whole process. After integration we have this equation. It means that T final over T1 equal T2 over T final, and finally we have Tf equal square root from T1 multiplied by T2. Let's count what is work W done by the engine. Total change of internal energy of these 2 objects with initial temperatures T1 and T2 equal this expression. It means that due to the first thermodynamical law, we have work done by all these processes equal due to change of internal energy, which is this expression. And that will be answer for question A. Question B. Find the minimum temperature TL to which the first object can be lowered. Solution. Due to the second thermodynamical law, we have minimum TL could be equal T1, which is 100 kelvins, because during this process we cannot get temperature less than minimum temperature of this object. In other case we could run process to run heat from lower temperature body to higher temperature body. And this is the answer for question B. Question C. Find the maximum temperature TH to which the third object can be raised. Because total change of entropy for whole 3 objects must be 0, we have a final expression that T1 multiplied by T2 multiplied by T3 must be constant during this process. Also, due to energy conservation, we have sum of temperatures must be constant. When we assume that third object has highest temperature TH, 2 other must have the lowest temperature T0. It means that we have these 2 equations, and using these initial numbers 100, now eliminating T0, we have this equation, and 1 root of this equation, it's obvious, that's TH equal 100. It means that rest we can convert to quadratic equation, and we have finally this expression, from which we have other 2 roots, 400 and 900. But because of energy conservation, 900 is not possible, So it means that the real answer is 400. It means that the final answer is for highest temperature is 400. That was a solution for question C. Problem A3. A ship can be thought of as a symmetric arrangement of soft iron. In the presence of an external magnetic field, the soft iron will become magnetized, creating a second, weaker magnetic field. We want to examine the effect of a ship's field on the ship's compass, which will be located in the middle of the ship. Let the strength of the Earth's magnetic field near the ship be BE, and the orientation of the field be horizontal, pointing directly toward true north. The Earth's magnetic field BE will magnetize the ship, which will then create a second magnetic field BS in the vicinity of the ship's compass given by this formula, where KB and KS are positive constants. Theta is the angle between the heading of the ship and the magnetic north, measured clockwise. Chords B and S are unit vectors pointing in toward the direction of the ship, bow and directly right of the forward direction, starboard respectively. Because of the ship's magnetic field, the ship's compass will no longer necessarily point north. Question A. Derive an expression for the deviation of the compass delta theta from north as a function of KB, KS and theta. Question B. Assuming that KB and KS are both much smaller than 1, at what headings theta will the deviation delta theta be largest? Solutions. To answer the question A, we need to represent in this formula vectors B and S in regular coordinates. Let's X be east direction and Y be north direction. In that case, we have B ort equal this expression and S ort be this expression. Now we can insert them in this expression for vector BS and find what are projections of this vector. In X direction we have Bx equal this expression, and in Y direction we have this expression. Here we also added magnetic field from Earth, BE. And now to find what is deviation, we just find what is a tangent of this angle. Tangent delta theta equal this relation. This is the answer for question A. For question B, assuming that KB and KS is very small, we can see that this tangent will be maximum when sine multiplied by cosine has maximum. And this happens for such angles like 45 degrees, 135 degrees, 225 degrees and 315 degrees. That's the answer for question B. A pair of iron balls placed in the same horizontal plane as a compass but a distance d away can be used to help correct for the error caused by the induced magnetism of the ship. Just like the ship, the iron balls will become magnetic because of the Earth's field BE. As spheres, the balls will individually act like dipoles. A dipole can be thought of as the field produced by two magnetic monopoles of a strength plus minus m at two different points. The magnetic field of a single pole is B equal plus minus m multiplied by vector r divided by r square, where the positive sign is for a north pole and the negative for a south pole. The dipole magnetic field is the sum of the two fields, a north pole at y equal positive a over 2 and the south pole at y equal negative a over 2, where the y-axis is horizontal and pointing north. A is a small distance, much smaller than the radius of the iron balls. In general, A equal Ki multiplied by BE, where Ki is a constant that depends on the size of the iron sphere. On the picture, a binnacle protecting the ship's compass in the center with the two soft iron spheres to help correct for errors in the compass heading. The use of the spheres was suggested by Lord Kelvin. Questions. Question C. Derive an expression for the magnetic field Bi from the iron a distance d much greater than a from the center of the ball. Note that there will be a component directed radially away from the ball and the component directed tangent to a circle of radius d around the ball, so using polar coordinates is recommended. Question D. If placed directly to the right and left of the ship compass, the iron balls can be located at a distance d to cancel out the error in the magnetic heading for any angles where delta theta is largest. Assuming that this is done, find the resulting expression for the combined deviation delta theta due to the ship and the balls for the magnetic heading for all angles theta. Solution for question C. Consider this picture, and on this picture let's check colored triangle with the black, red and green sides. The length of black side is A, angle between green side and the black side is phi, red side will have length A sine phi, and the green side has length A cosine phi. Magnetic field strength from one magnetic pole a distance d away is given by this formula. The sum of the two fields has two components. The angular component is a measure of the opening of the triangle formed by the two vectors, and since the two vectors basically have the same length, we can use similar triangles to conclude that A sine phi over d approximately equal B in direction phi divided by B. And finally we have B phi equal this expression or this expression, and the radial component equal to this expression, and after calculations approximate value is this one, where x equal A cosine phi. And finally we have radial component equal this expression. And this is the answer for both radial and angular components for magnetic field. For question C. Answer for question D. Note that the two iron balls create a magnetic field near the compass that behaves like that of the ship as a whole. There is a component directed toward the ball given by this expression, and a component directed toward the starboard given by this expression, where the factor of 2 are because there are two balls. Note that theta is the ship heading, while phi is the angle between north and the location of the compass relative to one of the balls. Thus, if the field is corrected for the maximum angles, it will necessarily cancel out the induced shear field for all of the angles, so that delta theta equals 0 for all theta. Effectively, this means placing the both to make KB equal KS. That was a solution for question T, and we answered for all questions for problem A3. Problem A4. Relativistic particles obey the mass-energy relation E square equal PC square plus MC square squared. The E is the relativistic energy of the particle, P is the relativistic momentum, M is the mass, and the C is the speed of light. A proton with mass MP and energy EP collides head-on with a photon, which is massless and has energy EB. The two combine and form a new particle with mass m delta called delta. It is a one-dimensional collision that conserves both relativistic energy and relativistic momentum. Question A. Determine EP in terms of MP, m delta, and EB. You may assume that EB is small. Question B. In this case, the photon energy EB is that of the cosmic background radiation, which is an electromagnetic wave with a wavelength 1.06 millimeters. Determine the energy of the photons, writing your answer in electron volts. Question C. Assuming this value for EB, what is the energy of the proton in electron volts that will allow the above reaction? This sets an upper limit on the energy of cosmic rays. The mass of the proton is given by mpc square equal 938 megaelectron-volt, and the mass of the delta is given by m delta c square equal 1232 megaelectron-volts. On the right we have table with the following relationship may be useful in solving this problem. Solution for question A. Here we can use this invariant E square equal PC square plus MC square squared. In such problems, better to use dimensionless speed of light equal 1. In that case, velocity v we can replace by relative velocity beta, and we can rewrite this equation for proton before reaction and for delta after reaction. This is the expression for full energy of proton before reaction and after reaction. But because we have energy conservation and momentum conservation, we can write these relations. We have to add energies for proton and photon here, and we have to subtract momentum for proton and momentum for photon, which is energy for photon over c. And because c equal 1, we have this relation. Now we can insert this expression to the second equation for E delta square, and that will give us this equation. Now let's simplify it. After squaring, we have this equation. EB square cancels from both sides, and now we can subtract from this equation initial expression for proton energy, and that will give us this expression. Now we can express energy for proton and momentum for proton using these relationships for relativistic energy and relativistic momentum, and we have this expression. And after all, we have function from beta, from which we can find what is relativistic velocity for proton before collision. We have 1 plus beta over square root from 1 minus beta square equal this expression, which is using all of these parameters which we need, m delta, mp, and eb, which we can call x. And from here we can find what is beta using x. That will be this expression. And the last point, we have to use expression for EP, which is relativistic energy. And finally we have energy of proton before collision, EP, equal this expression, where x equal this expression. So that was a solution for question A. Solution for question B. In this case, the photon energy EB is that of the cosmic background radiation, which is an electromagnetic wave with a wavelength 1.06 millimeters. Determine the energy of the photons, writing your answer in electron volts. Solution. Here we can use expression for energy of photon, which is equal to h nu, where h is a Planck constant and nu is a frequency, and the frequency equal lambda over speed of light. And finally, when we put numbers, we will get this number 0.00112 electron volts. That was the answer for question B. Solution for question C. Assuming this value for EB, which is this one, what is the energy of the proton in electron volts that will allow the above reaction? This sets an upper limit on the energy of cosmic rays. The mass of the proton is given by 938 megaelectron volts, and mass of the delta is given by 1232 megaelectron volts. To solve this question, we have to restore factor C in these two expressions, which will give us this expression. First, we have to count what is x for given numbers. Finally, for after all calculations, we will get this formula, and the answer is 1.4 10 power 20 electron volts. This number is also called GZK bond for cosmic rays. GZK stands for Grazen-Zatsepin-Kuzmin. So that was the answer for question C. Problem B1. Suppose a domino stands upright on a table. It has height h, thickness t, width w, as shown below, and mass m. The domino is free to rotate about its edges, but will not slide across the table. Question A. Suppose we give the domino a sharp horizontal impulsive push with a total momentum p. Question 1. At what height h above the table is the impulse p required to topple the domino smallest? Question 2. What is the minimum value of p to topple the domino? Solutions. For the first question, we can write equation for minimum required angular momentum. Because push is straight horizontal and this domino rotate around down left corner, so we have angular momentum after this push will be P multiplied by H. And if we require to topple this domino by minimum angular momentum L mean, means that if we increase height, we can decrease P. And the highest possible position for this point is small h. So it means that solution for question 1 is big H equals small h. So that's the answer for the first question. Second question. In the second question, we can use energy conservation. It means that if we push this domino with momentum P, we can add some kinetic energy. And this kinetic energy must be enough to overcome a change of potential energy for rotation. So we need to find what is the highest point for this domino and compare it to the initial height of center of mass. And that will be this potential energy change. Because initial height of center of mass is h over 2, and the final is the length of the half of diagonal of this domino, which is a square root from h square plus t square. So that will be total change of potential energy, and that must be equal to kinetic energy which we got from this initial push. This kinetic energy equal 1/2 L square over I, where L is angular momentum, which we got from this push, and I is moment of inertia of this domino around down left corner. Now we need to count this I. Using a parallel axis theorem, we can count this I. So that will be I0 plus mr square, where I0 that's a moment of inertia around center of mass, which is 1 over 12 h square plus t square, and r is distance from down left corner to the center of mass, which is 1/2 square root from h square plus t square. So that will be total I for this domino around this down left corner, which is 1/3 mh square plus t square. And the angular momentum equal P multiplied by H. Now we can insert all this angular momentum and also insert I to this formula. After that equalize delta U to delta K. And finally we got result for minimum P. That will be this formula. And this is the answer for question 2 from part A. Question B. Next, imagine a long row of dominoes with equal spacing L between the nearest sides of any pair of adjacent dominoes, as shown above. When the domino topples, it collides with the next domino in a row. Imagine this collision to be completely inelastic. What fraction of the total kinetic energy is lost in the collision of the first domino with the second domino? Solution for question B. First of all, when the first domino touch the second domino, it will happen on height big H equal square root from small h square minus L square. And this first domino has now angle with a cosine theta equal L over H compared to vertical. Now when we have absolutely inelastic collision, it means that both points of this attachment, they have the same horizontal velocity. And now we can count this horizontal velocity using angular velocities for both dominoes. Suppose that right after collision, these dominoes have angular velocities omega-1 and omega-2 respectively. It means that for the second domino, we have horizontal speed of this point will be omega-2 multiplied by height of this point, which is square root from h square minus l square, because it's the vertical. And for the first domino, we have this horizontal speed equal omega 1 multiplied by height h and multiplied by sine theta, which is omega 1 multiplied by the same square root from h square minus l square. We see that both horizontal velocities equal to each other. It means that angular velocities equal to each other too. It means that after collision, both dominoes have omega 2 equal omega 1. It means that after collision they have the same angular momentum, because they have the same moment of inertia and the same angular velocity. And because they have the same push with the same horizontal force, this force is horizontal because there are no friction between these dominoes. It means that if we have initial angular momentum for the first domino before collision, it will distribute some angular momentum to second domino, but it will lose the same angular momentum. So in total is the same. So it means that because they have the same angular momentum, it means that both dominoes have final angular momentum equal half of initial angular momentum for the first domino. And now, because total kinetic energy proportional to angular momentum square, we did half for the first domino, half for the second domino, and total kinetic energy will be half from initial. That's the answer for question B. Question C. After the collision, the dominoes rotate in such a way so that they always remain in contact. Assume that there is no friction between the dominoes and the first domino was given the smallest possible push such that it toppled. What is the minimum L such that the second domino will topple? You may work to lower non-trivial order in the angles through which the dominoes have rotated. Equivalently, you may approximate T and L much less than H. Solution for question C. First of all, we can include orientation of these dominoes using angles. Suppose that when we have left domino oriented like main diagonal vertical, we can count what is angle alpha between this diagonal and the vertical. And same thing for right domino, where we have angle this main diagonal and vertical, that's beta, and it's going to counterclockwise. And also we have angle phi, which is between diagonal and side of a domino. And now we can count what is the relation between alpha and beta when these dominoes touch to each other. Let's count the position for right up corner for left domino and the left up corner for right domino. Position for the upper right corner for left domino, x1 equal this expression, and for small angle that's h multiplied by phi multiplied by alpha. And x position for up left corner right domino, that will be this expression, which is approximately h multiplied by phi minus beta, because this t multiplied by 1 minus cosine phi plus beta, that's a second order compared to the first member, h sine phi minus beta. And the same thing we can talk about height of y coordinates. If we count only first order, we can neglect a second order and find that height is the same, that's approximately h for both corners. And because they are very close to each other, these top corners, and when one domino touch another domino, x1 approximately equal x2 in first order. So it means that initial distance between up right corner of left domino and up left corner of right domino is L. And when we rotate left domino by angle alpha and right domino by angle beta in opposite side, we have this relation between alpha and beta. It means that alpha equal L over H minus beta. And this we have to memorize and use for next step. Next step is to find what is maximum potential energy when these two dominoes slides to each other after collision. Potential energy for the first domino when it's rotate angle alpha from vertical position is this one, and with approximation for second order this one. And same thing for P2, for potential energy for the second domino. That's compared to bottom to the floor. And now we can add these two equations and find what is maximum for them using this relation. We take first derivative, use this relation, and finally find that the maximum potential energy will be for alpha maximum and beta maximum equal L over 2H. So we have to memorize this result for next step. Now we can use energy relation, and the energy we can count without all these coefficients, just using the common behavior of any functions near the maximum point. That will be this behavior. Suppose that if we have domino in vertical position, the potential energy equals 0. And in highest position, when diagonal is vertical, we have potential energy equal P. In that case, we can use this formula to approximate behavior for potential energy with the angle alpha for the direction of this diagonal. That will be a quadratic function for potential energy. And let's check. If we have alpha equal 0, we have a potential energy equal P, and if alpha equal phi, potential energy equals 0. So that's a true behavior. And the same thing we can say about right domino. Initial potential energy for initial position when left domino in vertical direction for diagonal and right domino in vertical position is P. Angle phi equal T over H. And also we can use angle psi, which is equal L over H. It means that when left domino just touch the right domino, alpha equal psi minus phi. And total potential energy difference between highest position and position when it touch the right domino will be this expression. And now all this potential energy go into kinetic energy when just before collision. And after collision we are losing half of this energy. So it means that we have a delta K of kinetic energy equal this one, half of delta P. And now we can write a relation for energies. Final potential energy when alpha maximum equal beta maximum, that will be this expression. Here we use alpha maximum equal beta maximum, and because L over H equal psi, we can rewrite this formula. This is potential energy for both dominoes in the highest position for potential energy after collision, and that must be equal to initial energy right after collision. That will be initial potential energy, which is P, minus energy lost during collision, which is this expression. And now we can cancel P and do this equation. Now, after cancelling quadratic members from right and left side, and using a relation that psi equal L over H and phi equal t over h, we can find that critical L will be equal 3 over 2t. It means that if L less than this 3 over 2t, right domino will not flip over. If it's greater, that will flip over. So that's the solution for question C in problem B1. Question D. A row of toppling dominoes can be considered to have a propagation speed of the length L plus t divided by the time between successive collisions. When the first domino is given a minimal push, just large enough to topple a start chain reaction of toppling dominoes, the speed increases with each domino, but approaches an asymptotic speed v. Suppose there is a row of dominoes on another planet. These dominoes have the same density as the dominoes previously considered, but are twice as tall, wide and thick, and placed with the spacing of 2L between them. If this row of dominoes topples with the same asymptotic speed v previously found, what is the local gravitational acceleration on this planet? Solution for part D. This part is independent of the others and requires only dimensional analysis. The speed v can depend on g, h, w, l. To get a quantity with a dimension l t power -1, we must take v equal dimensionless coefficient multiplied by square root from g multiplied by L, where L is some length made from H, W and L on the new planet. V is the same and L is twice as much, so G must be half as great on the new planet. That was a solution for part D. Problem B2. Bello College has a homemade 500 kilovolt 1D proton accelerator, designed and constructed by the students and the faculty. Accelerator DOM, assume it is a sphere, accelerating column, bending electromagnet, the accelerator dome, an aluminum sphere of radius A equal 0.5 meters. Is charged by a rubber belt with a width W equal 10 centimeters that moves with a speed Vb equal 20 meters per second. The accelerating column consists of 20 metal rings separated by glass rings. The rings are connected in series with 500 megaohm resistors. The proton beam has a current of 25 microampere and is accelerated through 500 kilovolt and then passes through a tuning electromagnet. The electromagnet consists of a wound copper pipe as a conductor. The electromagnet effectively creates a uniform field B inside a circular region of radius B equal 10 centimeters and 0 outside that region. On the figure, DOM metal rings of accelerating column, glass separators, electromagnet target resistor chain, only 6 of the 20 metals rings and resistors are shown in the figure. The fuzzy gray path is the path taken by the protons as they are accelerated from the DOM through the electromagnet into the target. Question A. Assuming the DOM is charged to 500 kV, determine the strength of the electric field at the surface of the DOM. Solution for question A. Potential for this sphere equal this expression. electric field near the surface of the sphere equal this expression. It means that the electric field near the sphere equal V over A, which is 10 power 6 volt per meter. That's the answer for question A. Question B. Assuming the proton beam is off, determine the time constant for the accelerating dome, the time it takes for the charge on the dome to decrease to 1 over E, which is approximately equal 1/3 of the initial value. Solution for question B. Solution for question B. Time constant for capacitor connected in series with the resistor equal to RC, where R is resistance for all of these resistors connected in series, and C is capacitance for sphere, which is equal to 4 pi epsilon 0 A. When we put all numbers, we will get for capacitance this amount. For total resistance for 20 resistors, we have 10 power 10 ohm, and finally time tau to discharge our capacitors in proportion 1 over E. We have tau equal this amount. So that's the answer for question B. Question C. Assuming the 25 microampere proton beam is on, determine the surface charge density that must be sprayed onto the charging belt in order to maintain a steady charge of 500 kV on the dome. Solution for question C. There are two main ways to discharge this sphere. One is a proton beam, which is 25 microampere, and other is through resistors, which we can use just Ohm law. That will be V over R, which is 50 microampere, and total current will be 75 microampere. And this current we have to produce using this charged belt. It means that we can find what is the surface charge density for this belt. We have a total current equal delta Q over delta T, and delta Q equal just a sigma multiplied by delta A over delta T, where delta A is how fast is this area moving, and area moving with the speed VB multiplied by width of this belt. And from this formula we can find what is sigma. So finally we have sigma equal current I over VB multiplied by W, where VB that's the speed of this belt and W is the width of this belt, and the answer is 37.5 microcoulomb per square meter. That's the answer for question C. Question D. The proton beam enters the electromagnet and is deflected by an angle theta equal 10 degrees. Determine the magnetic field strength. Basically, to solve this problem, we need to calculate what is the radius of this curve, because that's the radius of proton beams in constant magnetic field. And we can count what is the speed of this beam, and if we know what is radius of this arc, we can count what is the magnetic field. Let's do this. First of all, protons, they are not relativistic, and we can find what is the speed using acceleration by voltage 500 kilovolt. So we have kinetic energy for protons equal QV. When it moves in a magnetic field, we have other expression. Combining both expressions, we can find what is magnetic field B. So last step is to find what is the radius of this arc, and we can do it using some geometry. Because this arc crossing this circle on the right angle, we can draw this two radii for this arc, and from this geometry we can find that tangent theta over 2 equal b over r. And now we can put r from this formula in this expression for magnetic field and find that it's equal to this expression, which is approximately 0.0894 Tesla. That's the answer for question D. Question E. The electromagnet is composed of layers of spiral wound Cooper pipe. The pipe has inner diameter di equal 0.4 centimeters and the outer diameter d0 equal 0.5 centimeters. The copper pipe is wound into this flat spiral that has an inner diameter di equal 20 centimeters and the outer diameter d0 equal 50 centimeters. Assuming the pipe almost touches in the spiral winding, determine the length L in one spiral. Solution for question E. We can treat this question as not in 3D but in 2D. We can find what is area of this spiral and equalize it to area of the pipe. So we have from one hand this area equal pi over 4 multiplied by d0 square minus di square, and from other hand we have area equal length of spiral multiplied by outer diameter of this pipe. From here we can find what is L. And finally we have length of spiral L equal 33 meters. That was the answer for question E. Question F. Hollow pipe is used instead of solid conductors in order to allow for cooling of the magnet. If the resistivity of Cooper is ρ equal 1.7 by 10 power negative 8 ohm by meter, determine the electrical resistance of one spiral. Solution for question F. We can use a formula for resistance using resistivity, length, and cross-sectional area. That will be this expression, and after putting numbers we have 0.079 ohm. That was solution for question F. Question G. There are n equal 24 coils stacked on top of each other. Tap water with an initial temperature of Tc equal 18 degrees Celsius enters the spiral through the copper pipe to keep it from overheating. The water exists at a temperature of Th equal 31 degrees Celsius. The copper pipe carries a direct 45 ampere current in order to generate the necessary magnetic field. At what rate must the cooling water flow be provided to the electromagnet? Express your answer in liters per second with only one significant digit. The specific heat capacity of water is 4200 joules per 1 degrees Celsius per kilogram. The density of water is 1000 kg per cubic meter. Solution for question G. First, we can write rate of heat generated in these coils, which is I square R, and R equal number of coils multiplied by resistance of 1 spiral, which we already counted. Total power created in this stack of coil equal 3840 watt. This dissipated power must be equal to heat capacity for water multiplied by temperature difference, which is 31 minus 18, multiplied by density of water and multiplied by flow rate in liters per second. And now we can count this rate. That will be approximately 0.07 liters per second if we round it to the first digit. That was answer for question D. Question H. The protons are fired at a target consisting of fluorine atoms, Z equal 9. What is the distance of closest approach to the center of the fluorine nucleus for the protons? You can assume that the fluorine does not move. Solution. Conservation of energy for this process will give us that total kinetic energy of proton, which is QV, equal to energy of interaction between proton and the target atom, which is Z Q square over 4 pi epsilon 0 R. And from here we can find what is closest approach R. That will be approximately 2.59 by 10 power negative 14 meters. That's the answer for last question H.